I think this is due to fan, sir. Actually.
Which one?
Due to fan.
Due to fan. Oh.
Due to fan, sir.
Okay. So how to share it? No, whether I am audible or not.
No, audible actually. Sir, audible.
Okay. So how to?
Background sounds are there, sir.
That I will switch off. Yeah. Now it's okay.
Oh, sir. Yes, sir. Okay.
Yes, sir. How to share the file?
So, sir, I will tell you later. Just sir, 2 minutes, sir.
Okay.
So, good morning, dear participants, and good morning, Dr. Bimlesh Kumar, sir. He is the professor of Department of Civil Engineering, IIT Guwahati, and he has obtained his master and PhD degree from IIC Bangalore. And his research interest basically water resource engineering, and he has published papers in reputed journals, and he has 192 papers in reputed journals and 93 plus paper in conference proceeding. He has also published a book on by Lambert academic publication. Also undertaken various consultancies works related to water resource and hydraulics. Also, he is the reviewer of different international journals, and for his achievements, he has obtained Professor R.J. Gandhi Research Award by Indian Society of Hydraulics for his outstanding research contribution in the field of water resource. Also, he has obtained Best Thesis Award by IIC Bangalore. Also, he has a Kancha Reddy Award for his by Indian Water Works Association in the year 2006. So he has done a lot of work, and he is very dynamic, sir. Actually, I think all the participants will learn from something from Bimlesh sir. So I also thankful to Bimlesh sir for accepting our invitation to deliver a talk in research and practices in civil engineering. And today he will present on the topic sediment mining and its effect on river hydraulics. So thank you, sir. Thank you again, sir.
Yeah, thank you. Yeah.
Now you may present, sir, some just some suggestion to the or address to the participants, sir.
Yeah. Okay. First, how to share the slide. No, I simply open.
First.
Yes, yeah. Yes, sir. Now I'm seeing. Yeah. No. Yes. Now I have opened that slide. But I am not getting where is that slide turn off. Yeah, present now is there.
Yes.
Yeah. So entire screen. Yeah, this one. It is coming? Yes, yeah. Has it come? Error, it is showing some error has occurred. Yes, select PowerPoint slides. Now it is coming. Yeah, it's coming. But how to see the others? No, Pratik? Yes, okay. Okay, then, yeah. Okay. So shall I start?
Sure, sir. Yes, sir. Yes, sir.
Yeah, yeah. Thank you. Good morning, everyone. Thank you, Sujit and Pratik, for inviting. I'm going to present. Yeah.
Please on your video, sir.
Yes. How to?
Upon. Okay, sir. Okay, sir.
Oh, that is okay because I cannot see it anyway. So I will now
Okay, sir.
discuss the sediment mining impacts and its effect on river morphodynamics or river hydraulics in general. Okay, so first we will see the introduction. What is river mining or sediment mining? Basically, the mechanical removal of gravel and sand directly from the active channel of rivers and stream is known as sediment mining or river mining. And here I will share one information that after water, sand is the most used natural resources. So we have to see that it's important sand mining. When the sand and gravels are the most extracted group of materials, urbanization, basically housing everywhere, road construction, building construction, everywhere we are using sand, which is basically the coming from the river or alluvial channels. And we can see that in terms of quantity, it's around 30 to 50 billion tons each year. So that's a huge quantity. And recently, that is a Nature Geoscience paper. Ben Dixon time is running out of. So sand is very costly, very precious material. But when we do uncontrolled sediment mining, what will happen? Every day we are seeing that you see everywhere. You can see the tractors are lying there. They are skimming sand. It's uncontrolled or controlled, or government controlled. It's a legal part. We will not go into it. We will go into the hydraulics part, the slightly bit legal part. Okay, so before going to sediment mining, we will see that the type of river mining. First, it's a wet pit mining. You can see everywhere. And generally, I am living besides Brahmaputra. Every that the wet pit mining. You go into the river and excavate the sand. So what is when we excavate the sand, we increase the water table. The second type of river mining is dry pit mining. When you are in the non-monsoon season, so automatically water level gets and then we start mining the sediment. And the last is the bar skimming, with top layer of sand and bar gravel bar deposits. We are dredging, we are moving on the alluvial channel. So naturally, when we remove some sand from the alluvial channel or river, definitely there are going to be effects on several parameters such as morphological, which is channel's dimension, hydrological, discharge parameter. Sediments are a very important parameter for water quality or environmental pollution. Sorry. With a suspended sediment, we basically move the non-point source pollutant to one place to another place. So when we remove it, it may go into the whole water quality characteristics will go into change. So then the final ecological impact, we are increasing the water level depth. Definitely it is going to have some effect on the flora and fauna. Okay, so we will go one by one. Morphological effect. Morphological, as I have said earlier, no, it's a channel dimension. Generally we believe it's a channel. Morphology means channel dimension. What is going to affect on the channel dimension? Whether widths are going to increase, depths are going to increase. Definitely it is not regular, irregular. So there are different kinds of forces vortex will generate, that will increase the velocity, near bed velocities. Then what will happen to the nearby hydraulic structure? Suppose we put a bridge, and then upstream or downstream of a bridge we are doing the sediment mining. What will the effect on the bridge parameters, several things. And the long-term effect of sediment mining is the how much slope is going to be changed. When we start increasing day by day sediment from the river, what will happen to slope? What will happen to depth? What will happen to width? These are the major parameters. We all know that the sediment river is having 3 degrees of freedom: width, depth, and the slope. So definitely when we remove excavate sediment from the alluvial, definitely there is a effect on width, depth, and slope. So these are the morphological effect of sediment mining. I have just now told you that when you start mining from the system of a bridge pier, so what will happen to the bridge scoring and what will the effect on the bridge pier? So there are several examples where bridges have been damaged due to sediment mining. So where we can see that one from the California, Condolf, that is we have referred it. Then Portugal, one bridge has been failed due to sediment mining only. That is the Maharashtra one example is there. That the excessive sediment mining. Then you come to the Imperial bridge, is the Tamil Nadu. After intensive sand mining, you can see that the exposed, the foundation part is exposed. So undercutting is another example. Undermining and the failure of score protection systems such as collar. So these are the ecological effect of sediment mining. Now come to the hydrological and water quality effect. Generally, I don't go in the hydrological, so I will keep it very small in this part. Definitely, when it induces, when you do sediment mining in a river or alluvial channel, it induces a decline in the water table. Okay, so excessive mining, basically, when you start mining the sand, clay, they are having the filter properties. If you have any environmental pollutants, they act as a liner. Clay, basically, we all know that they use as a liner material also. So the pollutants may go into the groundwater system, nearby groundwater systems. Start mining the clay and sand. The pollutant due to mining, such as washing of mining material, these are the very local effect of water quality. But the major effect is that sediments, when we remove sand and when we remove clay, they are the filtering material for the environmental pollutants, different type of pollutant, source pollutant or non-point source pollutant. Okay, now recently, that is the 2014, Tejpal et al. Has published one paper. You can see the water decreasing trend of water level due to the excessive sediment mining. Now come to the ecological effect. Definitely, when you start removing sediment from the channels, flora, fauna, they are going to have some effect. These are the ecological effect of suspended sediment. Operation of mining can increase suspended sediment transport downstream, affecting benthic invertebrates and fish populations. In-stream mining,
Sir,
yeah,
sir,
yes, yes,
sir,
yeah.
please adjust camera. Actually, the photo It's not coming up. Adjust the camera, sir.
Now, I cannot see it. Is it okay?
Pratik, is it okay? Is it Pratik? Pratik? No, sir. Pratik?
It's not okay.
Okay, sir. Okay. And sir, sound is buffering actually. So earphone, sir. Have you earphone, sir?
Okay, I think no, that
Now okay.
it's
Photo is
okay, no?
okay, sir.
Yeah.
Sir, earphone, sir. You have.
No, I'm having in the office. No, I'm sound is audible, no?
Sound is audible. Sound is audible,
Okay.
but sometimes it is buffering actually. Sometimes.
Oh, no,
Okay,
there
okay.
may some household work, that is going on. So no, I have changed
Okay,
to
sir.
another network. It's okay, no?
Sir. It's okay.
Is it? Yes, yeah. So no, what I'm was discussing that's the ecological effect. So we all know that it's going to have effect on flora and fauna, and audible, no? So that rise in turbidity level in mining zone definitely, the smaller final particles they are going to have increase the turbidity level. This suspension of organic materials by decreasing this DO concentration, reduction of light penetration due to increased turbidity levels, vegetation, reduction of vegetation and increase the stream temperature. So these are some basic ecological effect of sediment mining. Okay, now just see the mining scenario in India. We all know basically living around nearby of any river. We all seeing day by day that tractors or trucks are lined up just to remove. It may be legal, illegal, but no. River mining is the largest source of sand in India. Basically, you just see that largest source of sand. So there are quartz, silica sand, no, but they are very costly. We cannot use in the construction purpose. So, despite the legal framework for sustainable mining practices, everyday court cases we are hearing, the industry gets most of its sand by illegally grazing the river bank and bank. So we can see that it's a huge problem, huge challenge to the government. As per the directives of Honorable Supreme Court of India, for carrying out mining in proximity to any bridge or embankment, appropriate safety zones should be worked on case-to-case basis. Well, that's not a universal criteria. Taking into the account the structural parameters, locational aspect, flow rate, etc. And no mining, you just see that no mining should be carried out in the safety zone. Okay. Also, as per the policy of sediment management and Ministry of Water Resources, Government of India, you just see that it's very important. No grazing or mining is allowed within 150 meter of any bridge crossing to safeguard the structural integrity of the bridge. Whether we are following, it's we are not the person to, but you just see several news clip we can see that drying rivers of Madhya Pradesh Narmada on the cups of extinction with 6 big dams, sand mining. Illegal sand mining is endangering bridges. See the economics time industry catching illegal sand mining is key to make mining pay in India. So now let's see, because of sediment mining, 365 bridges in Kerala in danger condition. Sand mining caused crack in bridges. That is the news from the Deccan Chronicle. It's 2017. Manali traced Himachal government admit illegal sand mining involvement. Just see that we all know that this is illegal, but that's easy to do it, because if you take no permission, you have to follow certain rules and regulation, and very difficult to follow it. So but these are there are various news clip for type of illegal sand mining. These I have shown you just a few. You can go through the Google. You see the problem is such it's a huge nature. Okay, but I will come to my area. That's a hydraulics part. Before going to the hydraulics part, we will see some review of earlier published of peers that effect of mining on channel hydromorphology, that include the hydraulics and that's morphological channel dimension parameter also. They just see that it's a very recent topic. We all know that it's happening from edges, but no, the hydraulics part, the investigation part starts very recently, 1989 first paper I'm seeing that. That's calling and done non-buzzing stations. Just see that there the findings. They found a river bed degradation of about 0.03 per year. So when you decrease the water level depth, suppose you start the whole thing of water resource management or water policy to have a certain amount of water at the downstream. So when your river bed is degrading, so you increase the risk of flooding. So next, Colin and Dane, you just see that the excessive extraction of wildlife pattern of bank erosion. Bank erosion, there is one very good example in the Manipur also. You have to mine the sand and then the bank part will go. The erosion part, the bank erosion part, the bank will collapse. Because it's irregular. When you have irregular forces, so different kind of forces acting there, the vortex part, this recirculation, the secondary current part, they are going to have effect on the bank erosion. So here they see that they found incision of 9.5 meter and that extended around 3.5 kilometer from the mining site. So huge. And they reviewed geomorphological data of 50 years of data in mining in several gravel bed river in northeast England. Roveria, that's they start study effect of intensive gravel mining during the period of 1956 to 87, and they're finding the estimated time for the Todera river to recover its pre-extraction bed level would be around 420 years. So number is not so good, but it's a 420. So illegal and illegal, we can assume it. They use sediment budget approach. And there are another Rinaldi and Westonia. The major part there is going to have incision, and then depends upon the how much we are doing it. Now those studies are the field study. Now we will see some experimental and numerical studies, which can be numerical experimental part, which can be done in the laboratory, and properly we scale up for the field level. Suppose we can generate some bed load equation for the mining. We can develop some scoring pattern for when happening, what will be the scoring pattern around these. So that part, when we keep the proper non-dimensional number, proper scaling parameter, so some effect we can see that can be basically imported to the field level also through experimental. So we just see the first experimental paper that hydraulic engineering, Lee et al. We generally use this paper as a Rosetta Stone. So because this is the first paper in the experimental on the experiment of sediment mining in a laboratory. So the mining pit, they created an open channel flow, and then some mining pit they created, basically the rectangular shape they created it, and their observation is that the mining migration of mining pit. So you construct a pit, suppose at x distance. After some time, it will go from the x plus 1, x plus 2. So they will increase in the downstream direction, and they develop some regression equations. So that part we are not going to see. And the Gill 1994, they develop, they do simulation of sentiment equation, which is the simple Navier-Stokes equation, suitably modified for the open channel flow, and they observed partial filling of mining downstream propagation with time. The findings of Lee and Gee, we can see that they are matching. No? They are almost of the similar nature. Mesa body that conducted experimental flume and field channel, how the mining pit will propagate in the downstream direction. Okay, then I will skip Bitcoin and Penders nearly for because the point here is that they also that the migrate pit will migrate in the downstream direction. So, but this is the very major finding. Some of the finding I will see from my laboratory also, that Nita Burman, I think Pratik may be knowing him, knowing her, that she did experiment to study the migration of mining pit. Now, earlier to Bandita Burman, no laboratory study was there. They used the rectangular pit, but we all know that no one is going to the river and mark the perfect shape and then start dredging it. They simply go to the river and start dredging. So definitely the pit, the shape of the pit will be irregular. It's no related to the rectangular or the very shaped, very regular shape. So Bandita Burman has done experimental irregular shape, and then also compared with the rectangular shape and the trapezoidal shape. And she found that the upstream of the mining pit, and that is the literature part also, mining pit is moving towards downstream. Correct. And the second is the degradation of channel bed. Channel bed is more prominent in the downstream of the mining pit. And then there are some turbulent parameters like Reynolds shear stresses, turbulent intensities, that become higher in mining region. I will discuss later that Reynolds shear stress and the turbulent intensity and downstream of it as compared to the upstream section. Okay. Now come to the bridge pier. We all know that bridges are there, and the location of bridges, we have to see the fact that wherever bridge is there, that section is, if you take the 50 years, 100-year return period data of their channel morphology, we generally construct bridge in the resign section. And width will be very narrow, so the construction cost will go down, the transportation logistics will be easy. But in the upstream of a bridge, suppose we start mining, what will happen to the bridge pier? The collar protection system, that like collars, different kind of scoring pattern, and what will happen to the foundation of a bridge? So these effect we basically recently we tried in our laboratory to see that. So before our laboratory, there are Q million from China. She done some experiment on this but she did not do that perfect segment mining. That's a head cutting. But if you see, then there will be no. So recently a visit from my guidance, he did experiment, and we will see his experiment also. Okay, this is the experimental flume in IIT Guwahati laboratory. You all welcome when things become normal. You all can come and see that. Teqip has also done on this flume, I think, on the scoring, bridge pier scoring. So this flume is 17 meter 1 meter width, 0.72 meter depth, and we took a sandbar thickness of around 0.20 to 1 meter, and we just see in this figure we created first a rectangular mining, okay, and then and downstream we put this here, okay. So we have used the acoustic Doppler velocity meter for 3D velocity recording, and get the bed level data. We use the URS system, so it directly gives the bed level, rectangular notches and the transducers, and bed level and water level recording for the other morphological parameters, okay. So this is the ADB part, how to filter it. Now just see that is the rectangular pit, and after 4 hours and 7 hours, we can see that how the migrating the pit is migrating in the downstream direction. The migration of mining in the downstream direction, and it increases with the flow velocity. Okay, and we can also see that the average bed shear stress at the downstream is very high. So that basically induces the sediment transport, and at the downstream we can see some kind of hump, that is the deposition after the bridge pier. So these are the some turbulent flow structure around mining pit. Turbulent flow, we all know that decaying infrastructure, but no, the real the turbulent flow is that where there is an imbalance between energy generation and dissipation. So when energy imbalance between energy generation and dissipation, then the different kind of effect will come, and that effect will not keep the fluid flow in a streamlined fashion. So the fluid started and behavior different from the streamline, and then that part we know that it's called the turbulent flow. And the turbulent flow, if you take any channel and measure the velocity, that will follow the logarithmic law. So we can see that the upstream it follows the logarithmic law, the log law we also saw, and we can see that the center of pit, section B, that's a 7.9. The stream-wise velocity observed to the negative. So it started the reversal flow. No, it will start. Earlier I have told you that bank erosion. So these are the parameters. When we strike the bank part, it can start the sediment movement. Sudden increase in the flow depth in the pit reduces the flow velocity, and deposition of sediment occurs. And when the flow leaves the pit and moves downstream, it again accelerates. Correct? And near bed velocity increases. It's a very good example of that. So when the near bed velocity increases, it is going to the bridge pier. Definitely know that this pier is designed with some other velocity. The new increased velocity is coming, so there will be some effect of foundation. Now we can see that the Reynolds stresses are the basically. No, we are not compatible with the Reynolds stresses. We can also say that a simple shear is that gamma was alpha. So that is the shear stress, basically GRS. So that is the Reynolds stresses in a turbulent term. We can say that although it is not equal, but the timing we can refer is just shear stress. Now we can see that the shear stress is increasing at section B, which is the middle of the pit, section C at the edge of the pit in the downstream direction. So the section B, which is the middle of the pit, is having the higher shear stress. And that basically having the effect on the movement. Now just see that this shear stress is greater than the critical shear stress or threshold shear stress. Threshold shear stress means the shear stress is required for a sand particle to move. or incipient, this is also called as incipient motion condition. So when we do experiment on the incipient motion channel, and then we will construct a pit, so then the inducing shear stress is in the critical shear stress. So definitely sediment particle will start moving. So contrary to obvious that the foundation will get exposed, the score is not going to be exposed, very big. But what is happening here, we will see it also. The width is going to increase. So with the sediment mining, it is not going to increase. Now just see that the 2 to 3 fold increase in shear stress is observed at section B, which is the middle of the section, and section C, which is the edge of the mining, which indicates high amount of sediment transport in the mining pit region. Okay. At the downstream of the mining pit, shear velocity or shear stress reduces around 14.5%. Okay, so then definitely there is going to have some kind of deposition at the downstream. Now, what's the bed load part? You will see when we have the shape 4, which is the irregular pit, and shape 3, which is the trapezoidal with the bank. When we put the trapezoidal with the bank shape, they are having the higher amount of bed load transport. What it means? It means that the reversal flow, the second part, they are going to have effect backs. Now, when we start mining in any river, irrespective of any hydraulic structure, the bank part will collapse. It has been observed that turbulence plays a very important role. So we all know that the sediment transport, and it significantly affect the processes which govern the morphological in terms of erosion and deposition of the sediment particles. Are you getting? Anyone? Hello? 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 Oh God, hang. Hello? Acha. You are getting it, no? Yeah. Yes. Yes, hello? Okay. You are getting it, no? It's not comfortable. No problem in that, no? Okay, now I will continue. Now, the real part of this presentation, what will happen to the hydromorphologic? Yeah. Yes. Okay. I am continuing it. Okay, so we can. Okay. No. Okay. So first, because if you just see, if you remember it, from the earlier slide, the Supreme Court said that no sediment mining is should be allowed within the 150 meter. So first we started investigation of the distance where we should start sustainable sediment mining. Some distance there will be say, because I'm going to use illegal or legal, so we require sand. So better to legalize it. So when you legalize it, you have to follow the certain rules, certain protocols. So that protocol is first to find where we should do the mining. Okay, and where you should not do the mining. So the different distance we created the rectangular flow pit and then find the effect of scoring pattern and different morphological pattern of bridge pier. Okay. So the results we can see that the river mainstream of velocity, that's correct, that the pit center, the downstream edges there will be erosion and flow depth will be increased, and flow approaching towards the pier with higher spatial acceleration, location 2. Now you see location 5 and 6 is the pier, and location 2 the flow is having very high spatial acceleration, and then you just see that there will be the 50% rise in average magnitude of negative velocities inside the score hole, indicating the stronger house vortex zone. So these are the some experimental result. We just see that no, definitely the law is not going to be followed without pit at location 1, location 2, and location 3. There are different stream-wise velocity. So now just see how the stream-wise velocity will look like when we start from the upstream pit to the downstream of the bridge pier. So the upstream is perfectly law. It's correct, but the pit center, you just see the some portion, it's a reversal of flow. Downstream pit is there is some hints of logarithmic following approach. It's a perfectly Lagrangian. But pier upstream and downstream, you just see that's a negative or reversal flow, which generates different kind of horseshoe vectors. So basically started the sediment scoring, and which gives the sediment scoring patterns, which is all we know that. Now upstream pit is to pit center, you just see the sudden pressure increase, reversal flow part is there, and downstream pit to approach the spatial acceleration is very high. Now we know some investigations slightly for the academic importance. So we found we go on investigate what will be the turbulent kinetic energy, how it is going to affect. Now we just see the flow approaches the pier with 50% more average turbulent energy after passing over a mining pit. So क्या no. It is saying that no connection secure. Okay, share the allowed, it's allowed. The window. Tag is coming. Okay. So what I was saying that the how much time I'm having, Pratik? No. Anyway, some time should be allowed. No? How much? Okay.
Sir, 11 up to 11:30, sir. 11:30, you may continue.
Okay. So what I was discussing that the turbulent kinetic energy, that is for the academic purpose, that flow approaches the pier 50% more average turbulent energy after passing over the mining pit. And Nezu and Nakagawa, they are the pioneers in this turbulent flow energy or turbulent segment transport and turbulent flow, the relation between those two phenomena, and they have some kind of equation, and we tried with Nezu Nakagawa. So this is for the academic purpose, that still whatever we are doing, it follows the Pierce result. Okay, so there are turbulent viscosity, it's eddy viscosity, we all know that there is a flow, not the fluid property, it's the flow property, and basically this is the link with the mixing length. We all know the mixing length If you remember, it's a log law or the Prandtl law of Prandtl mixing hypothesis, which basically started the engineering fluid mechanics. We don't know before 1940, 1915, I think, or 1909, I don't remember it. The Prandtl law, logarithmic, no, he developed it. Before that, Prandtl, we assume to have the zero viscosity and then do the real potential flow analysis, the very high term. But the engineering fluid mechanics basically comes with the mixing length theory or mixing length hypothesis. I think it's 1940 something. So that's the logarithmic law when we are having the laminar sublayer, smooth flow, rough flow. So there are different parts of the turbulent flow. Okay, so now you see that the turbulent viscosity, or in very general term it's eddy viscosity, is greater in the outer layer. Okay, in presence of a pit. Now, what do we mean by outer layer? Now, the open channel, now if you just measure the velocity, we will find there are three distinct trends are there. If you go very near to the bed, it's almost a straight line. That is because of the laminar sublayer. Now, inner layer up to Z by H 0.02, it's a inner layer. It is called inner layer where the logarithmic law will follow, and the outer layer, which is the parabolic beyond above Z by H is equal to 0.02, that is called outer layer. So the practical purpose of these three are that when we design any alluvial channel or any hydraulic structure, we generally take in the inner layer to the outer layer part and just see whether some properties are, what is the of some property. Like in this case, turbulent viscosity or eddy viscosity is higher in the outer layer. Thus, what it says that the mining pit acts as a source of turbulence. No source of turbulence when we say that it gives the imbalance between the energy generation and the dissipation. This is the turbulence, the imbalance between energy generation and dissipation. Otherwise, in the laminar flow, turbulence is there, but there will be perfectly balance between the energy generation and the dissipation. So this is the definition. So we all see that the bed shear stress at the location 4, it is now if you remember the bed shear stress from the open channel book, it's a gamma Y or gamma RSF, if you take the RH or gamma RHY SF, but that will be applicable when the flow is perfectly logarithmic. We know then we know all the trends like Reynolds shear stress, how it will vary. But in this case, when we start sediment mining a different kind of hydraulic structure, in presence of hydraulic structures, the logarithmic law will not be valid around the hydraulic structure, around the sediment mining pit. So there will be some different empirical equation to find the bed shear stress, and from that we have calculated the bed shear stress. One first is you calculate the turbulent kinetic energy from the ADB measurement, and then you back calculate the bed shear stress. Otherwise, there is another formula which is given by Staplin and Huntley, 1995. There is some empirical constant is there. Turbulent stresses there. If you remove the turbulent stresses from the background of undergraduate, we all know that the 9 stresses. So what are the effects? Generally, in the river flow, we take the axis symmetry case. We assume axis symmetry. When we assume axis symmetry, we need only two directions to work out two different phenomena, and then x and y or x and z, whatever. Can see that, and then we can calculate the Reynolds shear stress. In simple term, the shear stresses, how it is behaving in the presence of sediment mining and how it is behaving around the bridge. So we can see that the results will now When you don't have logarithmic law of following like mining pit and bridge pier, there is a universal form of logarithmic scaling which is also called as structure function. So we calculate the structure function around for the academic purpose and how it is behaving, what are the empirical constant. So different empirical constant to finding the higher moments basically. So and then we go into the vortex patterns behind that. We calculate the Strahl number. That the Strahl number we can see that the characteristics, dimension, frequency of vortex shading. The normal case it should be around to 0 as per the literature, and we just see that the bit is increasing. So increase in the frequency of vortex shading as well as Strahl number behind the piers, and it influences the turbulent characteristics behind the pier, also the vibrational forces on the pier, which basically is the major cause of waves. So continuous bit shear stress, this can. Now we will just see the effect of distance where we start mining pit, where we should keep the mining pit. So we did some experiment and we found that the steam bed instability is a function of Reynolds number as well as the distance between pit and pier, that's L by T, and that we can see the results from the results. Morphological effect of in-stream mining not localized in a particular region, but observed over the entire stream bed on the downstream side of mining pit. So this measure information excess erosion occurred inside the local score hole in the transverse direction, causing the exposure of pier. The stream bed in the approach zone as well as the behind the pier. Also, that basically what earlier I have said that the depth is not going to increase to. If you just see the width part, the width is loading is basically increased due to the change. So the results shows that the dredging is very close to pier is critical. So, it should be as far as we can keep from the bridge piers from the any hydraulic structure. Okay, so we did some experiment with the tandem. Nowadays, you don't have to replace it with another bridge by the already placed. So finally, the conclusion. We can derive from this experimental numerical and review work that erosion of bed downstream the pit is observed, irrespective of the shape of pit. Definitely, it will be there, it should be there, and the migration of a piston boundary with time and migration of speed of piston as increases with increasing bank value. In the bank value, and it is also observed the migration speed is more sensitive to property than the pit geometry. Okay, so irregular, but there will be some minor observation that when you have the irregular pit, it is having some effect on the bank stability also. The pit excavation acts as a source of turbulence to the downstream flow where the bridge pier is located. Flow passing over a pit excess beds here on the stream bed of the pier. Okay, so then we come to the second last. The dredging of a pit very close to pier is critical as pier exposure factor can reach as high as 1.6 and normalize the broad lowering at the approach can reach 0.4. Correct. So the final conclusion in this mining activity, especially in the proximity of the bridge pier, have the potential to erode the stream bed around the pier and it may contribute to its failure. Okay, so now I can sum up. I am ready to you can ask if you. Okay. Thank you. Yeah. Yes, no, if you are having any queries, no, you can ask.
Sir, after the completion of presentation, we will take up the query.
Yeah, presentation is over. Now we can take that.
Okay.
Yeah.
Okay, sir. Actually, participants have posted many questions.
Yes, yeah.
I am taking a few questions of them. Sir, is the artificial construction of hydraulic structure
Yes.
can affect the sediment transport, and what is the effect on it?
Definitely no, and just see what is happening. No, even you are putting anything to the river, no, the river pattern, the flow pattern is going to change. When you change the flow pattern, no, definitely there will be some effect on the stream or the sand stability, because suppose sands are on the line, they are lying on the with some forces. Now you put some external forces, either you will get a very no deposition kind of thing that's extra strong, or you will increase the sediment transport. No? So you put anything in the river, it will be having effect on the sand stability.
Okay, thank you. Sir, second question. I heard that you are working on bridge covering.
Yes,
So
yeah.
can you apply Leslie equation to estimate bridge covering? Is
Yes.
still we can use Leslie equation or any modified equation is there as seepage affects cover depth?
Just see what is happening now. We, as for IS code, if you remember it, we are using the modified Lacy equation. And if you go through the Morth code of Government of India, again we are using the Lacy, modified Lacy only. So, always scoring depth. No, when you start, suppose you calculate it from the Lacy equation or any other empirical equation, we always put some one factor of safety. So doesn't matter, we can use any equation, but as far as we are keeping some factor of safety, no problem. But people are still trying to develop. But it's very difficult. You cannot do that. Every river is having a different kind of morphology, stream pattern, the flow discharge. Yeah.
Okay.
Yeah.
Sir, how can protect erosion and affecting the environment?
No, I did not get it. No, can you repeat it? No, sorry.
Okay, thank you. How can we protect erosion in riverbed? Because erosion depositing the sediments particles in downstream and affecting the environment culture.
Yes, sir. How can you limit the bed erosion? Suppose bank erosion, we all know that we can put the vegetation, we can put the similar type of grounds, spurs are there. Those things are only for the bank protection. As far as we go through the book and literature, very difficult to stop the bed part, because that is difficult. You cannot do any modification at the bed level. So only thing is that we regulate the discharge. When we regulate the discharge, we know the discharge. If suppose some river flood is not coming, so there will be definitely there will be no bed erosion part. But as for present scenario, we cannot control the bed erosion. Bank erosion we can control it.
Sir, can you take another question, another one or two questions?
Yeah, no problem. I'm ready.
Okay, sir.
Yeah.
In experimental study, how was the model dimensions was decided, and how to confirm this dimension will give required result?
This is very good question. What is happening? You cannot do the one-to-one of real to the experiment. We also know that if we say there's some kind of scaling criteria, so we cannot do for the sediment sizes, or suppose width and the depth. Suppose 1.5 kilometer width is there and 10 meter depth is there at any section. When we want to do the experiment for that section, you just see the depth value. It should come into the millimeter. So then what we do, we generally go for the force similarity or the dynamic part, and for the scaling or the geometric part, what we do the distorted scale modeling. That's the acceptable approach, but exactly it is not the replica of the real system. See, but it will give you some information, then rounding this information with factor of safety, we can easily apply to the field level. So this is the real advantage of experiment. You cannot go to the field and start doing a experiment on the sediment mining, and you cannot measure the velocity. But when you do in a very controlled environment, which is a laboratory, you can get some kind of information how the velocity is going to be changed. How much scoring pattern can be affected. Yes. Yeah.
Okay, sir.
Yeah.
Sir, one request actually.
Yeah.
So this is not technical, but we think this is not technical question actually.
Okay.
So because our participants are generally faculty members, students, and field engineers are there actually, and maximum 90% are faculty and students.
Yes.
So we have seen your profiles there. You have published many papers,
Yes.
300 plus papers within a very short duration. I think so. So how to do research so that we can go up to that level? Because we are working in a state government college, just a state government.
Any
How to proceed that? How to do research so that
anyone can do that. It's not the great thing, no. Simply I was lucky, I think, but anyone can publish it. See, we have to see our limitation, where we can we have to use our limitation to the because when we know our limitation, then within those limitations we can work optimally. But when we don't know our limitation and then start doing that, then that is very dangerous. So once you know your limitation, then work around within your limitation, you will get it. And it's not a very great thing.
Thank you, sir, for giving a valuable suggestion. Also presented on the very informative session on related to Odisha engineering. And thank you for accepting our invitation for presenting in RPCE 2020. Also, I thankful to Pratik also because he has contacted with you. And I am the coordinator, but he has contacted with you. And I also thankful to Pratik. Also, I thankful to you. So spending some time actually,
definitely everything
to participate.
Everything becomes normal. You can come here and see that. That will be the better. Otherwise, I would have gone there and then do that. All these things, those things are very important. Hope it will come soon. Yeah. Okay then.
Sir, one special request. If you don't mind, sir, can you please share the slide?
No, I will give it to I will mail you to. I will mail this thing to you, and you can share it.
Okay, sir. Thank you, sir. So, thank you very much, and thank you, dear participants.
Yeah, thank you. Thank you. Yeah, bye.
Okay. Oh, like to okay.